Hi. Welcome to this week's lesson on properties of EMR. The way the course is going to look moving forward is we'll continue to use that Google Classroom. If you do have an issue kind of having access to Google Classroom, whether it's internet or whatever, please send me an email or message me in some way so that we can figure out kind of an alternative form of delivery for you. But each week is going to consist of a video where there's some instruction. There might be some practice questions, and then there will be assignment associated with that, with the idea that we're not going to spend more than like 2-3 hours each week on this course. Your assessment at this point is going to be in the form of weekly assignments. That's kind of where our mark is going to come from. So completing these assignments will be important because that's how we're going to be assessed. So you were kind of working on the electromagnetic spectrum, and I saw some of your projects, which I still need to mark, but they looked really good. So the electromagnetic spectrum includes all forms of electromagnetic radiation. So the kind we're most familiar with is visible light, because we can see that, but there's so many other forms outside of that. The thing is, they all behave the same way. So X-rays from an X-ray machine behave the same way as radio waves that we use to listen to the radio, or microwaves, which you use to cook our food and talk on cell phones with, or ultraviolet radiation, which gives us tans, or it can be used to disinfect things. So all of these different types of EMR behave the same way. And so today we're going to be looking at these different properties. Now remember, an electromagnetic wave is made up of different parts. There's the wave itself and where it's traveling. It has an electric field and a magnetic field. It has a wavelength. If we go back here, longer wavelengths are things like radio waves. Like they can be as long as like kilometers, units of kilometers we could use for like AM radio. And then we have very small wavelengths like X-rays or gamma rays, which come from the sun. They're the things that turn the Hulk green. And kind of everything in between. Microwaves, which are kind of in units of centimeters usually. So we have all these different orders of magnitude when it comes to these different waves. But all EMR displays these properties of reflection, refraction, diffraction, and polarization. And so this week we're going to look at these different properties in more detail. And your assignment will be based along identifying these properties at home. So the first property that all EMR, so regardless of size, so radio waves all the way to gamma rays and visible light, they display reflection. Reflection is what happens, so you see in this ripple tank here, when something strikes a barrier. So when light, or any form of EMR, even radio waves, even gamma rays, X-rays, when they hit a barrier that is reflective to them, they bounce off. So you see this wave coming in here. Some of it passes by. We'll talk about what that is after. But then the rest of it is reflected back. When things reflect, the properties of that wave don't change. So this is called the law of reflection. The law of reflection says that the angle of incidence, so the angle that a wave comes in, is equal to the angle of reflection. So that's the angle that light is reflected as it goes out. So the angle of incidence is equal to the angle of reflection. Now these angles are measured from what's called the normal. The normal is this perpendicular line to the surface, and we're measuring these inside angles. That's the angle of incidence, that's the angle of reflection. But the law of reflection is just basically when something hits something, it bounces off at the same angle that it's actually hit that thing. And that's probably something you're familiar with, even just throwing a ball at a wall. You know, you can kind of predict the angle the ball is going to come off of because you know the angle that it's going in at. And it's the same thing for any type of EMR. That is reflection. Another property of EMR is refraction. Refraction is what happens when EMR travels from one medium to another medium with a different density. So this can be going from like light into water, or from air into water, or from water into air. or it could be going from like glass into water or glass into air. But as light travels through different materials, it actually bends. You can see in this picture with this pencil, the pencil looks like it's broken, but we know that it's not. The reason why it appears this way is because light is actually bent differently in water as it is in air. And so it reaches our eyes in slightly different places, and we end up with this bent image. In this diagram, you can see this wave. You can see at this point where the medium changes. But as light goes from this medium into the next one, you see that it bends. So it's first off, and it also changes speed. You see that it slows down. So this medium is probably more dense. Light is taking longer to travel through it. So it slows down, and as it slows down, it bends. That is what refraction is. If light were to travel in the opposite direction, so from this more dense medium to this less dense medium, then it would speed up. And that's kind of how light travels in different mediums, and that's what refraction is. So this is a refraction tank. You can see that light is traveling from this laser from a more dense medium, which is water, and then traveling into a less dense medium, which is air. When we talk about the angle of incidence, we're talking about this angle here. So we always measure from this normal line, and this is the same for reflection. So this is my angle of incidence. It would be around like 35 degrees. My angle of refraction is measured from the normal here. So again, this perpendicular line, my angle of refraction is around 50 degrees. So the light comes in at a 30-degree angle and then goes out at a 50-degree angle. So when it goes from more dense to less dense, it bends away from the normal. If I were to switch the laser around, see if I can do that. Now you'll see that as I go from my less dense medium, where it's 35 degrees, into my more dense medium, it bends to 20 degrees. So going from less dense to more dense, light actually bends towards the normal. Diffraction is what happens when EMR or just any form of wave hits a slit, so a narrow slit. So we have these waves here and they meet this opening. What diffraction is that these waves actually, after they hit that opening, they spread out and they form circular waves behind it. You can kind of see in this GIF here, or GIF, I don't know how to pronounce it. What's happening as these flat waves hit this opening is they spread out and they behave like circular waves after that. And this is something that all EMR does and all waves do. It's very easy to see in like water waves. Like this is a wave tank. It's very easy to see in water waves what happens, but it's a little bit more difficult to see with EMR and visible light. The way that we see this with visible light is what's called an interference pattern. So diffraction happens to light when it hits a slit, and we see this most when we have two slits. When we have two slits, because those waves spread out, they spread out and then they actually start to interact with each other. Where the high part of the wave of one of these slits meets a high part from the other slit, we get a bright spot. Where the high part of a wave meets a low spot of another wave, they cancel each other out and we end up getting a dark spot. And so we end up with this pattern, which is called an interference pattern. And this interference pattern is evidence of diffraction of EMR. And all forms of EMR will do it. So here there's a laser shining on the wall. What I have here is a diffraction grating. This diffraction grating is a whole bunch of little tiny slits. You can actually see if you look through it. It takes white light and it separates it out into its different colors. If I were to do that with just one color, so with this red laser, when I put the diffraction grating there, you'll see that now I have multiple dots. I have a bright one in the middle, and then I have another set of dots on the outside. I can also do that with a green laser. So that I can take a green laser and put the diffraction grating in front of it. And you'll see that the dots are a little bit closer together than with the red laser. So green has a shorter wavelength than red, and so it actually diffracts more, whereas red diffracts less because it has a longer wavelength. So that's what a diffraction grating does. So diffraction is just a wave spreading out behind an opening. What happens with light is a little bit different in that it also interferes with itself. If you think about waves as being a whole bunch of crests and troughs, like a wave, where the crests meet up, so that the high points, they give us a bright spot, and then where the crests meet up with troughs, they give us a dark spot. You can see an interference pattern. If you were to make a little slit with your fingers like this, and then look up at a light, so look up at a source of light, you will see like dark and light bands. That is an interference pattern, just like what you saw on that screen, which is evidence of diffraction. The last property of light that we are going to look at this week is polarization. So you might have polarized lenses. Movie theater glasses are an example of this. But what they do is they allow us to filter light. So polarizing filters can really be thought of as like gates, where light is normally non-polarized, so it's present in all of these different directions. What happens when light hits these polarizing filters is only light in particular directions can get through. So this polarized wave is striking this filter, and it only allows vertical light to get through. As this vertical light travels on, if it were to hit another filter that's actually orientated the other way, it's perpendicular, now no light is going to get through that filter. Because there are no horizontal light waves that can actually get through. So on the other side, it would actually be very dark. Polarizing sunglasses work much this same way, where they filter out light in specific orientations. So we get all of this light reflecting off of some of these surfaces, and it lets through light that's kind of orientated up and down, but it reflects out light that's horizontal and has a glare. So light that is kind of oscillating in this direction cannot get through that filter, whereas light that's in this direction is allowed to get through the filter. So that gets through, but this is bounced off. So I have on a pair of 3D polarizing glasses. So each of these lenses are polarized, and then I have another polarizing filter here. You'll see that when I bring it in front, if I leave it in a certain orientation, nothing really changes. But if I were to rotate it, you'll see that that eye gets very dark, and you can't see through it. So polarizing filters are kind of like gates, where this is maybe a vertical gate, so vertical light is getting through it. If I were to take a filter and tilt it this way, so now it's a horizontal gate. So when this is a vertical gate, light gets through it. But when I tilt it and it is a horizontal gate, now none of that vertical light can get through. So the first lens is going up and down, the second lens is going that way, and it cancels out all light. So that is what polarization is. The way that these glasses actually work is one of these is up and down, the other one is side to side. When they shoot the 3D movie from the screen, you get the side to side light in this eye, and then this eye gets the up and down light, and they're slightly different images, and then your brain puts them together into a 3D picture.